Okay, in this video we're going to look at the one sample design. Again, what we'll do is we'll take a look at how this relates to the general linear model that was depicted in the previous lectures, and you can see how to conduct this kind of analysis. So let's open up our data. So if we go to our data from the handbook examples, we're going to go to the one sample t-test example. So we've got two variables in this, mass and height. I'm just going to focus on mass for this video just to keep it relatively short, but everything that we do with mass can be done with height as well. So to start off with, let's look at our linear regression model. So as I said, if we go to regression and go to linear regression, we can add in the variable that we're interested in here. So if we add in mass, then essentially what we get is, as was described in the lecture, an intercept-only model. We have no x values, we have no predictors, and therefore we only have an intercept in our model. And essentially, the coefficient for the intercept is equivalent to the mean of that variable that we're looking at. So if, for example, we went down to statistics, clicked on descriptives here, and it calculated the mean for us, you'll see that the two are equivalent to one another. Now, typically, the test that we would use for this kind of analysis is what is known as the one sample t-test. Now to do that, if we come up to the t-tests option here, we can select one sample t-test. It's just loading up there. And if we take mass and add that into the variables column, you'll see here that we get a t statistic, some degrees of freedom, and a p-value. Now let's quickly scroll up and have a look at some of the outputs on our linear regression as well. As you can see, we have a t statistic for our intercept on our model as well. Now, what this t statistic is essentially it is our model's coefficient divided by its standard error, which is the same as essentially the mean divided by its standard error in the case of this model. So our t statistic for our one sample t-test is the same as what is calculated from our intercept-only linear regression model. If, for example, again, in the t-test, we click on descriptives, you see again, we get exactly the same, a mean value of 72.913. These are all equivalent. One sample t-test is essentially just an intercept-only linear regression model. The same applies also again if we rank transform the data and perform a rank transformed intercept-only model and a rank transformed one sample t-test. Or strictly speaking, actually, this would be a signed rank test because if you've got negative values, they need to be negatively valued and signed correctly as well. I'm not going to show you that here. We're just going to move straight on to the one sample analysis to try and keep the remainder of these videos nice and short and easy for you to follow. Okay, so let's have a look at our one sample test then. So typically what we would do is if we were interested in a one sample design, we have a single group, we've collected some data from it, so for example mass and height in this case, and we might be interested in testing to see if the sample of data that we've got differs from some reference value. And this is what you can do in JASP with the one sample t-test. So under here we have the various different tests we can do. We have the student's t-test, which is our typical one sample parametric test. We also have the Wilcoxon signed rank, as I said, and we also have something called the Z-test, but you don't need to worry too much about that for the moment. We then have the option to change the test value. And what this does is it tests the null hypothesis that we compare our data to. So in this case, we've currently got it set at 0. So all this is saying is if we assume the null hypothesis that that body mass is actually 0, then what's the probability that we would observe data this extreme or more extreme? And as you can see, we get a very, very low p-value. Because, of course, everyone's got body mass larger than 0 just by dint of existing. What we'd probably be more interested in is comparing it to some reference value. So let's say, hypothetically, that we've got a sample of males here and the average body mass for males in the United Kingdom is 80 kilos. We can change this to 80 here, and then we can update our test to see whether or not our sample of males significantly differs from that. So this is now, you can see the t-value has updated because we're testing against a different hypothesis now, and you can see it's also updated here to specify which hypothesis we're testing against. Now, what we can do is we can also select some additional statistics and create some plots to visualize this so we can understand what that looks like. So, for example, we can add in a ligation estimate, which tells us how much does our sample differ from the mean that was provided? And you can see here that there's a difference of around 7 kilos. We can also add in some plots for that. So we could add a descriptors plot here, which shows that relative to the reference value of 80, our sample is significantly lower than that. Now, this isn't a particularly great plot to look at. It's obviously a truncated y-axis. It's not that aesthetically pleasing. There are some much nicer plots we can do. And in fact, I'm going to skip straight to what is called the rain cloud plot, which is a wonderful way of presenting this kind of data. What a rain cloud plot does is it, in fact, if we change it horizontally, it looks even more like a rain cloud. We have a density which shows the distribution of the data. We have a box plot which shows all the typical features of the box plot, including the median, interquartile range, minimum and maximum values, and then you actually have the raw data plotted with a nice jitter across the y-axis, or in this case x-axis because we flipped it around, and you have the reference value here. So you can compare how that data looks compared to that reference value. So if you're doing a one sample test and you've got some reference value to compare it to, then I would definitely recommend doing this. For those of you who maybe want to look a little bit more advanced into this, you can also consider an additional module called equivalence t-tests. Now, with equivalence t-tests, not only do you have a single value, but you can set a range of values to see whether or not your sample is equivalent to some range of values. So, for example, if you have a normal data for a particular variable that you're interested in, and you conduct a one sample study design, and you want to know whether the data you've collected lies within the expected range for normal data, then you can use equivalence t-tests for that. There are some nice videos on the JASP YouTube page showing you how to do those kinds of analyses. Hopefully this has been useful, and again has shown you the kind of equivalence between that general linear model and the named tests, such as the one sample t-tests here. As I mentioned, there is the non-parametric version of this, which is the Wilcoxon signed rank test, and all that does is essentially produce a signed rank transformation on the data, and then essentially does exactly the same thing, does this intercept only model, which is what we call that one sample t-test. For example, if we select that now, we also get a Wilcoxon statistic here, and we see whether or not essentially the median is different from that reference value. So again, if you've got that kind of data which would be better compared using a non-parametric test, then it's very, very simple to do so.